Hey everyone, today I want to talk to you about how we can defend distributed systems embedded in things like factories, planes, trains, and automobiles from attacks with a new approach called bounded time recovery. I've been working on this with Ida Roth, Brian Sandler, Andreas Heberlin, and Lin-Thai Suong Tan. In this work, we focus on cyber-physical systems, which are systems that use sensor data to change the behavior of actuators. For example, let's take a look at this chemical vat that has attached to it a temperature sensor and a pressure sensor. It has a burner that can add heat to the system, a pressure valve through which the chemical flows in and out, an emergency alarm, and a live stream data monitor. The set of sensors and actuators are connected together through a set of control nodes. On these control nodes run applications. For instance, this application uses pressure sensor data to control the alarm. Similarly, there are several other applications that are used to control the other actuators. Cyber-physical systems can be attacked, much like traditional distributed systems. Let's say that node 4 is compromised. Well, in this case, let's say the attacker now wants to control the burner, so they send a new type of signal to the burner which causes the flame to increase in size, thereby increasing the heat and pressure until a catastrophe occurs. Therefore, we need a fault tolerance technique for cyber-physical systems that can tolerate more than just simple crash faults. One option is to use a BFT protocol, which can completely mask faults. However, there's a substantial cost because BFT needs at least two F+1 replicas. However, CPS are often resource constrained. For instance, they often use low-power CPUs. If we were to try to reschedule BFT onto this example system, then we would need to schedule all of the replicas shown in gray, but only a subset of them are actually schedulable in our system, meaning we wouldn't be able to schedule all of the applications that we want to. So what else can we do? Well, many cyber-physical systems do not actually need to perfectly mask all of the symptoms of a fault. Let's take another look at our burner application. Normally, the temperature will be reading within a small range when correct operation is occurring. When a fault occurs, the burner will increase its flame output, and this will result in the temperature steadily rising up until a point at which some kind of catastrophe occurs. After the catastrophe occurs, the system is non-recoverable. But during the time between when the fault occurs and when the catastrophe occurs, we have a kind of recovery period during which, if we're able to resume correct operation, the system is recoverable. So our approach in this work is to propose a technique called bounded time recovery, which guarantees that so long as there is no fault within the past t seconds, correct operation will occur in the system. The recovery period is the period of time between when the fault occurs and t seconds after the fault, during which arbitrary behavior is allowed. Recovery must occur within this recovery period, after which correct operation resumes. There are two parts to providing the BTR guarantee. The first is scheduling F+1 replicas for every task in order to tolerate up to F faults. The second is recovery, in which we change which nodes are responsible for which tasks in response to a fault. Let's start this example system in the root mode, which means that there are no nodes or links faulty. A mode maps to a particular set of tasks and their replicas assigned to a particular set of nodes. Let's look at the particular data flow of task 4 sending data to task 5 on node 2 and its replica on node 4. Now, when node 2 is compromised, task 5 on node 2 will misbehave, but task 5 on node 4 is able to catch when the misbehavior occurs. In response to the misbehavior, the tasks can be migrated as a mode transition occurs, and the data will be rerouted through the set of healthy nodes, leaving the faulty node isolated. Providing the BTR guarantee is non-trivial. We need to identify when a fault occurs so that we can recover by the right time. We need to identify which node is faulty, and at the same time, we need to prevent incorrect attribution, in which a node believes that another healthy node is faulty instead of the actually compromised one. We need to prevent false negatives, where a faulty node is able to convince the rest of the system that everything is okay, even though it's not. And we want to prevent false positives, in which no node is faulty, and yet some node believes that other nodes are compromised. We need to do so while providing a guarantee that we can bound the detection and recovery time, even when the adversary tries to delay detection or recovery. Now that we've introduced BTR and how they can be used in CPS, let's delve a little bit into details. First, let's talk about our model. We assume that all faults are observable Byzantine faults, meaning there's some kind of externally visible effect of the attack. We are not concerned with bit flips occurring on some obscure node that will never affect anything. We assume a synchronous system in which the continuous time spectrum is divided into discretized rounds. We do not assume all-to-all connectivity between nodes because cyberphysical systems often do not have such topologies and use a combination of buses and point-to-point links. At maximum, n-1 of the nodes in the system may fail. And finally, we have a mixed criticality system in which the least critical application might be dropped when a fault occurs in order to ensure that the most critical applications continue to run. This raises the question of how we can catch faults to trigger mode transitions. Well, we need at least one healthy node to catch a fault, so if there can be a fault, there must be at least f+1 replicas. In a quick example, here we see that task 5 runs on both node 2 and node 4. Both copies run the same program. They use a set of inputs to an addition program to produce an output. Now, the two replicas cross-check one another to make sure the other one is behaving correctly. If node 2 misbehaves, then the copy on node 4 is able to catch the misbehavior and declare that node 2 is faulty. However, it's not quite so simple. Let's say node 3 is compromised and node 2 catches node 3 misbehaving. Node 3 can simply make a counterclaim that node 2 is misbehaving. We resolve this issue by making sure all messages are signed. So the input to a function will be signed and sent along. The inputs will then be used to produce an output. In both replicas, the output is also signed. The two outputs can be compared, and if they do not match, this constitutes evidence of misbehavior, which can be used to notify others of the need for a mode transition. So far, so good. But what about omission faults? That is, replicas cannot verify that a message was not received by another node. Our solution to this is to allow a node to declare a link to be faulty unilaterally, so long as it is one of the endpoints of that link, and it signs the link fault declaration. So in this sample topology, let's say that task 1 and task 2 are in a data flow where the data passes through some intermediate node. If the intermediate node is compromised, it may omit to send the data from task 1 on to task 2. In this case, the node that task 2 runs on might notice the omitted message and declare the link between it and the intermediate node as faulty. In this case, the system will perform a mode transition and might reroute the data through another healthy node. Notice here that if the adversary tries to exploit the fact that it can unilaterally declare link faults, it will only be isolating itself as it declares more and more of its own links as faulty, in which case the system is still making progress because less data is being routed through the faulty node. There still leaves the complexity of what happens when compromised nodes start working together. Let's take a simple linear topology and look at them through time, divided into discrete rounds. In round 0, node 1 sends data to node 2, and node 2 forwards the data to node 3. If node 1 is compromised, it might omit the data. In this case, instead of sending data to node 3, node 2 is expected to send a link fault declaration. However, if node 2 is also compromised, it might omit sending the link fault declaration. But since node 3 knows that it should expect either data or a link fault declaration in round 1, then it can make a deduction about who is faulty after round 1 completes. Now, there's a lot more complicated strategies that adversaries can employ, but we don't have enough time to get into them, so you can read more about how the system works in the paper. There's a lot more that goes into setting up REBOUND. For instance, we require that all messages must be signed for proper attribution and to prevent forgery. We also require heartbeats to be sent by each node in every round to all other nodes in the system so that we can ensure that the entire system operates in a consistent mode. We don't have enough time to get into the details for all of these, but you can read more in the paper. Now that we've briefly covered how our approach actually works, let's take a look at some of the sample results. Now there's quite a few experiments that we ran, but we don't have enough time to talk about them all, so we'll limit ourselves to discussing a few key results. First, let's take a look at what the costs of REBOUND are. For this experiment, we used synthetic workloads applied in randomized network topologies and compared REBOUND with and without optimizations. The unoptimized case shows that even at a 100-node system, the overhead is still manageable. For instance, in the leftmost graph, for a 100-node system, we're consuming less than 20 kilobytes per link per round. We can see when we add the optimizations in that we scale much better, and the differential between the two approaches only grows as the system size increases. So we can see that the overhead is a manageable amount, and the scalability is greatly improved when we use optimizations like multi-signatures. Next, we'll look at our running example implemented in a real embedded platform. This is an oscilloscope reading of an experiment where no protection was given to the system. The yellow, blue, and green signals represent PWM signals that were sent through the 3 actuators shown on the left. The vertical red line shows where the fault was injected, and we can see that after the fault was injected, the adversary sent garbage values to the pressure alarm, and that's why the pressure alarm will no longer work after the fault. In contrast, when we use rebound, we can see that after the fault is injected, garbage values are sent to the pressure alarm only for a short period of time, after which correct operation resumes. In the process, we drop the monitor application, but remember, since we have a mixed criticality system, we can drop the least critical application in order to ensure that all of the most critical applications continue to operate. So the takeaway here is that our approach can both detect and recover quickly in a real embedded platform. Bringing it all together, we have seen that bounded time recovery, or BTR, is a new approach to defending distributed systems against attacks. It is low cost since it only needs f+1 replicas to tolerate up to f Byzantine faults, and after a fault occurs, within a bounded amount of time, BTR guarantees that the system will both detect the fault and recover from it. BTR is a good fit for cyber-physical systems, which are often resource-constrained and do not need to completely mask all of the symptoms of a fault due to properties like thermal capacity or inertia. REBOUND is the first concrete algorithm to use a BTR approach to protect against Byzantine failures. It does so by designing a multi-mode system, in which the system transitions between modes in order to respond to faults. REBOUND is able to keep the most critical applications running in the system by dropping the least critical ones as computational resources become more scarce as more faults occur. Thank you.